All right, today we're jumping into a real classic. It's a favorite in coding interviews, and it seems simple on the surface, but the solution, oh, it's just incredibly clever. So let's get right into it.
So let me ask you this. Picture a list of numbers, all nice and sorted from smallest to largest. Your job is to find two numbers in that list that add up perfectly to a target number. Seems easy enough, right? Well, that's where the fun begins.
Okay, here's the official problem statement, just like you'd see it in a coding challenge. We get a sorted array of integers, we'll call it numbers, and we need to find two of them that sum up to a specific target. The really important things to notice here are that the array is already sorted, and our answer needs to be the positions, the indices of those two numbers.
Now, these are the rules of the game, and this is where it gets interesting. First, the array is sorted. That is a massive clue. Second, the indices we return have to be one-indexed, which is a little tricky since programmers usually start counting from 0. But the real kicker, the rule that makes this a truly great puzzle, is that last one. You can only use constant extra space. That means you can't just create a big new list or hash map to store stuff. Nope. You have to solve it right there, within the space you're given, which means you've got to be clever.
So how in the world do we solve this with all those rules? Well, we use a really beautiful technique called the two-pointer approach. It is the perfect tool for this job, and you're about to see exactly why.
The core idea is actually super simple. Just picture it. You put one pointer at the very first number in the list and a second pointer at the very last number. Then you just start walking them toward each other, one step at a time.
Let's break down that logic. You've got your start pointer at the beginning and your end pointer at the, end. You add up the numbers they're pointing at. Now, if that sum is too big, how do you make it smaller? Well, since the list is sorted, you have to move the end pointer to the left, towards a smaller number. And what if the sum is too small? You do the opposite. You move the start pointer to the right, towards a bigger number. You just keep doing this dance until, bam, you hit the target.
Theory is one thing, but let's actually see this thing work. We're going to walk through a classic example, step by step, so you can see the pointers in action. All right, here's our setup. Our list of numbers is 2, 7, 11, 15, and our target is 9. So we put our start pointer, S, right at the beginning on the number 2. And our end pointer, E, goes all the way to the end on the number 15. First move, we calculate the sum. So 2 plus 15 gives us 17. Our target is 9. So 17 is way too high. Now, according to our rules, what do we do when the sum is too big? You got it. We have to make the sum smaller. And the only way to guarantee a smaller sum is to move that E pointer one step to the left. So we shift it from 15 over to the next largest number, which is 11. Okay, let's try this again. New sum, 2 plus 11. That's 13. We're getting closer, but 13 is still bigger than our target of 9. So we just followed the same exact logic.
We take that E pointer and we move it one more step to the left. Now it's pointing at the number 7. Notice our S pointer hasn't moved an inch this whole time.
And here it is, the magic moment. We calculate the new sum. 2 plus 7 equals 9. That's it. That is exactly our target. We found our two numbers, and the search is officially over. So what do we return? Well, the start pointer is at index 0, and the end pointer is at index 1. But wait, remember that rule from the beginning? The answer has to be one-indexed. So we just add 1 to each index, which gives us our final answer, the array 1, 2. Perfect. So now that we've seen how it works, let's take a second to really appreciate why the solution is so darn smart. It's not just correct, it's incredibly elegant and efficient. You know, if you were to actually write the code for this, the whole thing would be powered by one simple line, a while loop that just runs as long as the start pointer is to the left of the end pointer. That little loop is the entire engine, driving the pointers inward and guaranteeing we only have to look at our data one single time.
So let's really break down why it's so smart. On the logic side, it takes massive advantage of the fact that the array is sorted. Every time we moved that end pointer inward, we didn't just eliminate one number, we eliminated all possible pairs involving that number. And that logic directly leads to its incredible efficiency. It solves the problem in what's called linear time, because we only make one pass through the data. And since we only needed two simple pointers, it uses constant extra space, which perfectly satisfies that really tricky rule we started with.
So if there's one thing to take away from all this, it's that the two-pointer method isn't just a random guess. It is a systematic, intelligent process of elimination.
By starting at the biggest and smallest possible values, every single move we make, whether we're moving the end pointer in or the start pointer out, is methodically shrinking the search space, closing in on the one and only correct answer. And that leaves us with one final fascinating thought. This whole beautiful, efficient strategy hinges on that one crucial fact: the array is sorted. So what would you do if it wasn't? How would that change your entire approach? Well, that's a whole other puzzle for another day. Thanks for diving into the two-sum problem with me.